So in this video we're going to look at an example where setting up the iterated integrals to calculate the area is actually going to require that we set up two iterated integrals to calculate the area we are interested in. So it says find the area of the region bounded by f of x equals the opposite of x minus 2 squared plus 4. So I have a parabola in vertex form. G of x equals negative 3x plus 6, and y equals 0, which is just the x-axis. So the bounded region, I have a graph of it here. We're bounding ourselves using the parabola, the x-axis, and the line minus 3x plus 6. So the bounded region for which we are interested in finding the area is the part of is the region that's inside of the graphs of those three functions. And so here's the issue. We can calculate the area by either doing dx dy, or we can choose to calculate the area by doing dy dx. So let's first look at the more complicated case, which in this case is probably the dx dy case. So if we're calculating the area dx dy, our initial bounds of integration are running in the x direction parallel to the x-axis. And so what we can see is for a while the left bound of integration is going to be the line and the right bound of integration is going to be the parabola. But when we get to this intersection here, as we move from left to right, the control of the bounds hands off, because now the parabola is the only thing controlling the left and the right bounds of integration. So what you wind up needing is two integrals, one for the y interval over which the line is controlling it on the left and the parabola on the right, and then a second interval for which the left side of the parabola controls the left side of the horizontal line and the right hand side of the parabola controls the right hand side. So if we were to set this up, we would need to set up two iterated integrals. So this would be, they'll both be dx dy. So let's deal with the first one, the first part of it first. We're running from the line to the parabola. So the line that we have right here is the line y equals minus 3x plus 6. But I can't just slap that in here, because if I'm integrating, sorry, I'll do this first. If I'm integrating with respect to dx first, I need to have x equals a function of y for my upper and lower bounds of integration. So what I have to do is solve this for y. So for example, we could get 3x equals 6 minus y, and then divide both sides by 3. That would solve it for x. So the left bound of integration would be the line x equals 6 minus y over 3. So down here we get 6 minus y over 3 as our left bound of integration. And then the right bound of integration, we really have the parabola sitting up here. This is the parabola y equals the opposite of x minus 2 squared plus 4. And we would need to solve this for x. So we would subtract 4 from both sides, multiply both sides by negative 1, which would reverse the order of this subtraction, and then take the square root of both sides for what's left, and that would give us plus or minus, depending on whether we are dealing with the left or the right hand side of the parabola, equals x minus 2, and then add the 2 to both sides. We get x equals 2 plus or minus the square root. So for this upper bound of integration, because it's the right hand side of the parabola, it would be 2 plus the square root. So I would get 2 plus the square root of 4 minus y. And then we would have to say what is the y interval over which the left and right controls are bounded by these two functions of y. Well, that happens when we're running from y equals 0 to y equals 3. So here's the y interval running from 0 to 3. And then the rest of it is handled over the y interval from 3 to 4. So from 3 to 4 on the outer interval where my dy's are, I'm moving left to right, being controlled on the left by 2 minus the square root of 4 minus y, and on the right hand side by 2 plus the square root of 4 minus y. So I have to set up the two iterated integrals to calculate the area of that interior region. If I run dy dx first, things are going to be easier, I think, but I still am going to need two iterated integrals. And the reason is, starting here, I have to run vertical slices first, so run parallel to the y-axis first. So the line below is the lower bound and the parabola above is the upper bound of integration. But when I get to the vertex at x equal 2, now suddenly the vertical slices are going to be controlled by the x-axis and the parabola. So I have to hand off control. So what we can do is say, hey, I'm going to need two integrals to calculate this area. They're both going to be dy dx. This first one, I'm going to run from the line to the parabola, and now I don't need to solve anything because this, these are y equals guys right here. So y equals the line, and the line is just minus 3x plus 6. Run from the line to the parabola, and the parabola is the opposite of x minus 2 squared plus 4. And then what's the x interval over which that happens? Well, right here we start at x equal 1, and the vertex starts at x equal to 2. So we're going to run between the line and the parabola over the x interval from 1 to 2. Then once we get to x equal to 2, how we control things needs to hand off, because between 2 and 3, so the x running from 2 to 3, there's our vertical slices are running from y equals 0, or the x-axis, up to the parabola, and the parabola is just minus x minus 2 quantity squared plus 4. So I need two iterated integrals to calculate the area of the bounded region. The rub is, and this is pretty common, the rub is that one of the pairs of iterated integrals appears to be easier to deal with than does the other. So it isn't uncommon to be in the situation where you've got to choose, am I going to do dy dx or dx dy? And a lot of times the choice will be driven by which choice seems to give me the easiest integral to work with. Sometimes we have to make our choice based on whether we're able to integrate the function that we wind up with inside the double integral. So your choices are driven by a lot of factors, but in this case I would say it's pretty clear to me that this one is going to be more fun to deal with than the one that has the square roots floating around in it.